Hello, students. So, in this lecture, we will specifically focus on flow stress, but we will start uh, with an expression that in any metal working case, in any metal working, the forming stress or the pressure forming stress or a pressure uh, can be expressed as P is equal to sigma naught bar Gf and H as a function of C. Now this uh, sigma naught bar is the flow resistance of the material. And it is actually appropriate for it is actually appropriate for a uniaxial plane strain. So only when we are considering an uniaxial plane strain, so for that strain, the stress required or the resistance to that stress to cause a uniaxial plane strain is the flow resistance. And now this flow stress is a function of temperature, strain, and strain rate. Temperature, strain, and strain rate. Secondly, uh, this GF, it stands for the friction, at the interface of the tool workpiece, and this factor, it is actually a geometrical factor. uh, it is based upon the geometry of the tool and the geometry of the material or the metal which is undergoing deformation. Now the metalworking usually gives a large plastic strains. This, when we are talking about metalworking, there are large plastic strains involved in the process. And so the flow curve or the flow resistance, that is the main objective of this lecture. The flow resistance has to be measured for uh, when the true strain has gone to a value of 2 to 4. That means the elongation or whatever deformation has taken place 2 times the original well. Now, apart from these large plastic strains, the metalworking process also involves high strain rates. Salem dot, which is say of the order of 100 per second. You need to have a lot of metallic, a lot of force applied to achieve these sort of strain. It physically 100 per second. It means that it is the material is getting elongated 100 times per second. So we can imagine how much force needs to be given to achieve such sort of plane strain, and such sort of plane strain occurs in the case of metalworking. Now, apart from these aspects, as initially we have shown that this resistance, it is a function of temperature as well. So, a lot of metal working process, they take place at elevated temperature, because that makes the dislocation movement much easier. So, we can say that the flow stress, the stress causing the plastic deformation, this flow stress is strain rate sensitive, but at elevated temperatures it is independent of strain. So this is the reason why when we are determining the flow stress, it has to be carried out at a controlled condition, where the temperature and the strain rate are constant, or we can have, one needs to take a note of these two aspects when we are determining the flow stress. Now, the true stress, true strain curve, means Shannon T sigma T. This is the true stress strain plot. They are different from engineering stress and strain, because in the case of true stress we are considering the reduction in cross section. We are considering this fact. Now, these true stress, true strain curve determined from tension test is of limited usefulness, because this necking, this process of necking that indicates the onset of plastic deformation, it limits uniform deformation to two strains less than 0.5. So when the two strains has gone 0.5, so there is no longer no longer uniform deformation taking place. That means the cross section, due to the reduction in the cross section, when the true strain has reached half its 0.5, that means the material has been elongated 50 times of its original length. So at that point of time, the uniform deformation no longer exists. So this true stress strain plot is of no use. And this is actually more pronounced at temperature being raised, and that is hot working. And now in the hot working, the strain hardening, there is low rate of strain hardening. The strain hardening means that that when you are allowing sufficient amount of stress, so there is a movement of dislocations, and sometimes this stress also causes new dislocation to form. So when the dislocation density, let's not go into that, it reaches a certain value such that the movement of dislocations, they are hampered. So we can, this is called strain hardening. That means due to application of external strain, the material has got hardened. That means due to new formation of new dislocations and increased value of dislocation density. Now what happens in the case of hot working is that since the temperature is high, there is a low rate of strain hardening taking place. This is why, because even if the dislocations are formed due to temperature, the strain caused by dislocation gets released due to this high temperature. So due to this, so the rate of strain hardening is low, and as the strain hardening is low, so plasticity is more, the movement of dislocation becomes easier, so the necking takes place earlier. So what was initially was being formed at 0.5, now the neck of the true strains, the necking in elevated temperature, in the hot working condition, the necking starts to take place at a strain of 0.1, that is 10 times. Yes, 0.1 times, 10 times the original length. Earlier it was 50 times, now it is 10 times. Now, also this necking, the process of necking, so this is a dog bone shaped. It's being tensile stress, so concentrating on this region, what has happened is that there is reduction in cross-sectional area. This is called necking. It means dislocation movement has started. Now, due to this necking, a complex stress state arises, which causes a complex stress state, because the dislocation movement have started. And what is interesting is that it locally it raises the strain rate. So initially the increased temperature caused a decrease in strain rate, so that caused easier nicking. However, this nicking caused a local raise in the strain rate. So global, we can call it in this way, a global reduction or overall reduction in the strain rate, it gave rise to a local enhancement of strain rate. This was all about tension. Now if you move to the process of compression, so now what is compression? How is it different from tension? So now instead of applying the stress in this direction, we have now changed the direction of stress in the opposite direction. Let's consider a cylinder which is being compressed. Now in this case, these tests can be carried out at a strain excess of 2.0. There is no problem of taking involved, provided the material is ductile, that means it is a metal. So there is reduction to 2.0, means it has reduced to half of its area, half of its initial dimension. So there is no aspect of ticking, or there is no problem with the nicking that has caused. However, there is a friction between the specimen and the anvil. The concept of friction can take place between the force with which, or the tool which is used to compress, is called an anvil. Now, if we consider the diameter of the cylinder as DO, the initial diameter, and initial height as H0, and it has been compressed to height say D, diameter say D and H. So usually D square H, D0 square H is equal to D square H. It is simply because of the fact that the volume is same. Volume is same. Now, if we look at little pictorially, so say this is the original cylinder with original diameter D0 and H, which has been subjected to compression. Okay, so this compression is causing say H0. H0 is getting reduced. So reduction in H0, since the diameter volume is constant, it is causing the diameter D to increase. So as the diameter is getting increased, so this process leads to the activation of the frictional forces. because they will oppose frictional force between the system. I mean, if you are holding the metal in this direction or whatever way you are holding, and there is a system in which this cylinder has been kept, so there will be a friction between the system and the, because the material will try to increase, so it will oppose the outward plastic flow of the metal. So that's how this GF factor that we told initially, this factor comes into the picture. Now so the friction which occurs in the part where the metal is in contact with the system, whereas there are regions where the metal, the outward flow is undisturbed. So more often it is at the middle where the flow is undisturbed, whereas where the connections have been made, or where the metal or the specimen has been held, is called the anvil. There actually the frictional forces are the highest. In the middle it's quite free. So there is a, so we get a paralleled specimen profile. And in fact a cone shaped profile is being formed. So we plot axial load provided and if you plot it with the reduction in height, so this is the specimen, it's clamped at this end. So this is axial load sigma, and there's reduction in height taking place. So the reduction height profile usually is like this. But interestingly, if you take the D0 versus H0 ratio, so if you vary this ratio, that means you vary the diameter versus, or you can, actually it's also called as the aspect ratio, you can call it. That means you are having either, you're having a sample, so a high value of D0 by H0 sample, if it is high, it would look much more flatter, where if it is low, it will look like this, much thinner. Now we can have different plots. So a higher value of D0 by H0 will give you a higher slope. So you have three different slopes. So this is the way this D0 by H0, based upon this D0 by H0 ratio, we'll have different plots. So what we can say about is that the flatter is the sample, and the more axial load is required to cause reduction in height. This is because you are getting less free flow area, and more area is clamped with the surface, with the holding regions. That is why a higher axial load is required. Now these cone-shaped zones, they approach and overlap, because so it's being called a cone-shaped mainly because of the fact that see, this was the initial cylindrical shape, and this is the free flow region, or the friction is more active in this region, or the friction is less active in this region, more frictional forces is at the clamps. So it will be like this cone shape. That is why it's called the cone shape. They are considering this as a cone from the base. Okay, so that's why they're calling it as a cone shaped profile. Or cone shaped zones, you may call it. Now this is called barreling. I'll put it this way. Barreling, or a barreled specimen. Barreled specimen. Now, one way to minimize this barreling and non-uniform deformation is to use a low value of D0 by H0. By low value of D0 by H0 means a thinner sample, not a flatter sample. So the specimen is usually kept in this range, a low value, then you can reduce this your non-uniform deformation to some extent. And there is a practical limit, and that limit used is 0.5. Because below this limit, one could argue that why not less than this, because below this limit the specimen buckles. Instead of getting barreled. Now, the true flow stress, that means the stress required to close the plastic deformation without friction, because if we consider the friction into consideration, so that is a property which is external to the specimen, so it will, whereas true flow stress is more of an internal specimen, so we need to consider without friction. So this can be achieved if you plot D0 by H0 for several values of reduction and extrapolating each curve to D0 by H0 is equal to 0. If this is what we can do, we get the flow stress. The true value of flow stress can be achieved. This is one way by which the barreling effect can be minimized. Now, another way of having or getting the exact or the flow or the true flow stress is by reduction of the friction. Reduction of the friction, that is reduction of the factor GF. It can be minimized by using smooth hardened platens. So this is more of a geometrical manipulation that one or the manipulation and finishing of the specimen under test. So it should be smooth, hardened, flattens, and then grooving ends. This is interesting because so grooving ends. The reason for having grooving ends is that these grooving ends can hold the lubricants for a longer time. So what it means is that if this is the specimen which is being clamped here somehow, and so if we have a grooving ends, so and if we lubricate these grooving ends by some oil to reduce the friction, so grooving ends will hold the specimen for a longer time. So that's how we can reduce the friction. Now our Teflon sheet, when we are using a cold deformation, and glass for hot deformation, these are the effective lubricants in the case of compression tests. So with this reduction of friction or attempt reduction of friction, for a strain of 1.0 can be achieved without the barreling effect. So up to this strain, the barreling effect can be prevented. Okay, now coming to little mathematics fast. So if we assume that there is no friction, so there is a uniaxial compressive force, the force uniaxial compressive force. It's say this is P and it is equal to sigma naught into A. This is the cross-sectional area and this is the stress applied. So the true compressive stress produced by this force P, so let's call it a capital P. So the true compressive stress we are calling it is the small p. This is the true compressive stress. So this is equal to 4p by pi d squared. It is simply the load divided by the area. And if you consider the d0 versus H0 ratio into consideration. So this is can be said to be equal to 4p h divided by pi d naught square h naught. So where d naught and h naught are the initial diameter and height of the cylindrical sample. So let's write it once again. P is equal to, initially it was 4p by pi d square. Now it has been replaced by 4p h divided by pi d0 square into h naught. So this d has been replaced by the initial diameter, whereas a factor of h by h naught has been introduced. So there is a change in height. The diameter is the same. The height is changing from h0 to h naught due to this compression. So the two compressive strain compressive strain is C is equal to natural log of change in dimension, that is h0 by h. Now if the compression test is done at a constant crosshead speed, the true strain rate continuously increases with deformation. Now as the strain rate increases to 10 to 10 per second, severe control testing machine can be modified to maintain the constant true strain. Now for metalworking, strain rates for 1 to 10 to the power 3 per second. The only equipment for providing a constant true strain rate is the CAM plastometer. CLAM plastometer. So a plane strain compression test wants to visualize. It is very difficult to conduct on a thin sheet, but it might be useful to machine the specimen. So it can be done. So the plane strain compression test. So in this step, what is done is that a band across the width of a strip is compressed by narrow pattern. So it is like this. So you have specimen like this, and then like this. So there are two platens. This is the upper platen. This is the lower platen. This is the specimen. So there is a deformation in the direction of the platen motion and in the direction normal to the length of the plates. So there is a deformation in two perpendicular regions. There is deformation take place in this region, and also in this region. Now the slip line field theory. Has been applied for this plane strain compression test. And it has been found that the axial compressive stress axial compressive stress is simply the applied load divided by the contact area of the specimen. Is applied load divided by the contact area of the platens. So that means these platens, which are used to deform the shape. So it's the contact area of the platens. And this is so. As long as the ratio of indentation thickness to the platen width is larger. So it's as long as the ratio of indentation thickness, the thickness at which the platens are acting, that is considered to be the indentation thickness, to platen width. So that means if these are the platens used for the compressive stress, this region, this one, This region is called the indentation thickness. Whereas the platen width is B. So when this T by B ratio, indentation thickness with width of the platen, is in the range of 1/4 to 1 by 2, then as said, the uniaxial stress is simply the load divided by the contact area of the platens, provided it is in this range. Now, by keeping the ratio of T by B in this range, it is possible, it has been found that it's possible to cause deformation of 90%. Now, another requirement that to maintain this plane strain condition, is the width of the specimen. So this is the specimen, so its width. This width W taken, and the width of the platens must be greater than 5. That means it should be, the specimen should be 5 times more wider, 5 times or more wider than the platens. Only then this plane strain condition can be maintained. So the true stress strain determined in the plane strain compression test may be expressed as, so this is the strain, this is load divided by width of the specimen into B is the width of the platen, and corresponding to strain is again T0 initial indentation depth versus the final indentation depth.